Welcome to the Explainer. Today, we're decoding a hidden language, one that pretty much powers our entire modern world. From the movies you get recommended online to the very graphics on your screen. We're talking about the language of data itself.
I mean, have you ever really stopped to think about that? How does your phone recognize your face? How does an app translate languages almost instantly? Or how does a video game render these incredibly complex, beautiful worlds? A computer can't see or hear the way we do, right?
Well, the answer is, it translates our world into a special language, a language of numbers, space, and direction. And that language is called linear algebra. So today we're going to learn its basic vocabulary and its grammar. Okay, let's dive right in.
So just like any language, this one has its nouns, the basic things it describes. And in linear algebra, these fundamental building blocks are what we call scalars, vectors, and matrices. They're how we take real-world data and represent it with numbers. And what's really cool here is how these concepts build on each other. We start simple, with the scalar. That's just a single number, like, say, the temperature. Then we can level up to a vector, which is a list of numbers. You can think of it as a point in space or maybe an arrow with a direction and length. And finally, we get to a matrix, this big grid of numbers that can represent an entire image, or a whole data set of user preferences, or even the rules for completely transforming space itself.
Okay, so we've got our nouns, we've got our data packed into vectors. What's next? Well, in any language, you need verbs to actually do things. So how do we measure these vectors? How do we compare them and see how they relate to each other?
The first, most obvious question you might ask is, okay, how big is this vector? In the world of linear algebra, we have a specific word for this concept. We call it a norm. It's just a formal mathematical way of talking about the magnitude or the length of a vector.
And what's fascinating is that there's more than one way to measure distance. The L2 norm, that's the one we're all familiar with. It's the direct, straight-line path, as the crow flies. But then you've got the L1 norm. It's totally different. It's often called the Manhattan distance because it's like you're a taxi driver who has to stick to the city grid, block by block. Both are totally valid ways to measure a vector's size, and which one you use just depends on the problem you're trying to solve.
So measuring one vector is great, but what if you've got two of them? How do you compare them? Well, that's where the dot product comes in, and it is an incredibly powerful tool. It manages to boil down the entire complex relationship between two vectors into a single number, and it does it by looking at the angle between them.
So what is this one number really telling us? Well, think about it like this. If the angle between the vectors is 0, they're perfectly aligned. They're working together, like two people pushing a car in the exact same direction. If the angle is 90 degrees, they're orthogonal. That means they have 0 influence on each other, kind of like one person pushing the car forward while another pushes it from the side. And, of course, if the angle is 180 degrees, they're in complete opposition, working directly against each other.
Okay, now let's get to the really fun part, matrices. We've learned the nouns and the verbs of our language. Now we're getting into the grammar that actually creates meaning. This is where linear algebra really starts to tell a story.
Now, it is so important to stop thinking of a matrix as just a static, boring table of data. That's not what it is. I want you to think of it as a machine, a function, a set of instructions. When you multiply a vector by a matrix, you're not just doing some random math. You are feeding that vector into the machine, and the matrix transforms it. It stretches it, shrinks it, rotates it, or flips it into a completely new vector.
So if this matrix is a transformation machine, we need a way to measure how much it changes things, right? And that is exactly what the determinant does for us. It gives us a single number to describe the whole thing. So if you transform a simple square with a matrix, the determinant tells you the area of the new shape. A determinant of 2 means the area doubled. A determinant of 0.5, the area got cut in half.
And this right here, this is a hugely critical idea. What happens if the determinant is 0? It means the matrix squashes all of space down into a lower dimension. Imagine a 3D object getting completely flattened into a 2D shadow. When that happens, you've lost information. You can't unflatten a shadow to get the original object back. The transformation is totally irreversible.
But as long as that determinant isn't 0, guess what? We have an undo button. For just about any transformation matrix, we can find an inverse matrix. This thing does the exact opposite. It's a reverse transformation that takes your stretched, rotated vector and puts it right back where it started. And this is the absolute key to solving all sorts of systems of linear equations.
All right, so amidst all this complex stretching and rotating and shearing, there's actually a hidden, deeper structure. A matrix transformation isn't just random chaos. It has a fundamental character, a true essence, kind of like the soul of the language. And we can actually find it.
I want you to imagine a transformation, like a powerful gust of wind blowing across a huge field, and all over that field, you've placed millions of tiny arrows, or vectors. When that wind blows, it's going to push them all around. Almost every single one of them is going to get knocked off its original line and end up pointing in some new direction.
So here's the profound question. In all that swirling change, is there any arrow, any special vector that despite that powerful gust doesn't get knocked off its path? Now, it might get stretched longer or maybe shrunk down shorter, but it still points in the exact same direction it started in.
And the answer is yes, there are. And these incredibly special vectors are called eigenvectors. You can think of them as the hidden skeleton of a transformation. They represent the true axes of the change, the stable directions that hold steady while everything else shifts around them. And the amount they get scaled by, that stretching or shrinking factor, that's called the eigenvalue.
Let's make this real with an example. So for this particular transformation matrix, there's a special direction along the line of the vector 1, 1. Any vector on that line gets stretched out to 3 times its original length, so its eigenvalue is 3. At the same time, there's another special direction, 1, negative 1. And any vector along that line has an eigenvalue of 1, which means it stays completely unchanged. These two directions basically define the soul of this entire transformation.
So, who cares, right? Why does any of this matter? Well, it turns out that finding these essential directions, these eigenvectors, is fundamental to how so much of our technology actually works. It's how Google's original PageRank algorithm figured out the most important pages on the web. It's how machine learning models find the most significant patterns in massive, messy data sets. It's basically how a computer understands the core features of a face. Look, we've really only just scratched the surface here, but you now have the core vocabulary and the basic grammar of this incredibly powerful language. And the key thing to remember is that this isn't just abstract math. It's a fundamental toolkit for making sense of the world, for structuring information, and it's a powerful new way of seeing everything around.